Thank you. So first, I want to thank the organizers for inviting me and the IPAM for hosting this, this workshop. And I'm not a robot, okay? It's here. All right. So today I want to, well, okay, I had a choice between various subjects, but I thought the one with Vertex model in the title was better. So I apologize for those of you who might have seen this or a version of this. So I'm going to talk about Arctic curves or Vertex models. And so I want to give you a sort of overview. So I'm not going to concentrate on one model, but I will give you a list of models. Now, these models will share the property that they can all be described in terms of paths, okay? So you all know about dimers, domino tilings, various types of tilings. All those models can be described in terms of non-intersecting paths. And the non-intersection is the crucial basic property that makes all those models fermionic, like physicists would say. But we're going to go beyond that and consider also models that actually include not just non-intersecting paths, but what's called osculating paths, that is, paths that are allowed to bounce against each other. And of course, with a special weight attached to this possibility. And that will give us some, I think, more interesting physics and asymptotics. And so, as far as asymptotics are concerned, we are going to first observe an Arctic phenomenon on those various models, depending, of course, on the choice of boundary conditions. So if you choose your boundary conditions wisely, you will observe an Arctic phenomenon of some kind, which is the emergence of frozen regions and separated from liquid regions by, fluctuation regions that become curved in the continuum limit. And we are really going to concentrate on the curves themselves. I know here you're all about fluctuations, but today it's just about curves. And to investigate those, I will describe and use explicitly the tangent method, which was developed by Colomo and Sportiello a few years ago, and show you how efficient it is to not just treat fermionic models, but also these interacting fermion models. Okay, so, okay, I lost my screen here. Interesting. How do I get my screen back? Okay, so the first thing is we all know about domino tilings. So you want to cover a domain of Z2, of a square lattice with domino tiles 1 by 2, 2 by 1. And the first thing is to transform the problem into a problem of non-intersecting paths. So here is the dictionary, right? So you have 4 possible dominoes because there's a natural bicoloring, underlying bicoloring of a square lattice. And so we associate to those 4 dominoes pieces of path. And I like to think of this as going from left to right. So your path always starts in darkness and ends up in light, right? And so if you're enlightened first, you don't need to go anywhere. So there's no path there. All right. So this is, of course, the domino tilings of the Aztec diamonds expressed in terms of those paths. And then it's really child's play to calculate the partition function, not resorting to anything fancy, no Castelline matrix, nothing. Just use the good old Gesolviano theorem, which tells us that the partition function for non-intersecting paths with a bunch of starting points and another bunch of ending points is just the determinant of single partition function or single paths going from the ith point to the jth arrival point. Okay. Another example, which I borrow from the literature of the alternating sign matrix saga, actually, it's called the rhombus tilings of a wholly hexagon with 1/3 turn symmetry. Okay, so imagine you have a big hexagon, but it's not quite regular. It has edges n and n plus 2. n, n plus 2, n plus 2. And that allows for the middle to have a small hole here, you see, of a triangular shape. And then you want to enumerate rhombus tiling configurations that are 2 pi over 3 invariant, right? So you rotate by 2 pi over 3, you should have the same configuration. So it's kind of easy to see that it just amounts to cutting a fundamental domain and gluing this side with this side so that you have a cone, right? So you're enumerating non-intersecting paths on a cone. And the objects that are enumerated by this are called descending plane partitions, and it's an old story involving Andrews, who invented those objects. But the great thing is that once you compute pretty much in the same way as I showed you the Aztec diamond, you find this nice number, which is also identified as the ASM number, right? The number of alternating sign matrices. And so there's been a conjecture that a bunch of objects are enumerated by the same number, that's this number. And so descending plane partitions are also enumerated by this number. Example 3, so that's kind of a square lattice version of this guy, right? So we had a almost regular hexagon, hole in the middle, and some rotational symmetry, okay? So now we have an almost regular Aztec square, but not quite. As you can see, I have some steps here, and more fun, there is a cross missing in the middle. So if you count the number of square faces, it's even, so it's nice. It means it's probably tileable. And here is an example of tiling, right? And now you're going to impose, well, the natural 2 pi over 4 rotational symmetry of this system. And therefore, again, try to tile a cone, right, in this fundamental domain. So how do you do that? Well, you use my previous bijection, right, with paths. So now you have non-intersecting paths that start and end at, well, comparable positions. Here, there's a shift of 1 because there's a hole in the middle which shifts everything by 1. There's some small condition that the paths cannot start with a vertical step. But apart from that, you're just, again, applying the SLVNO. But now you have to sum over all possible positions of these points, right? So this is the view of what you're doing, right? So it's a nice cone with a hole in the bottom, right? Very dangerous. And here are the numbers. So this is my first sequence of numbers. When you enumerate this thing, you find this sequence of 1, 3, 23, etc. Right? So this thing, right? Okay. Example 4, still domino tilings, but now of something that looks like a triangle on top of which I put a hat which looks like an Aztec diamond. Okay? So this shape is interesting for a reason you will find out later. Now you can just take my word for it, right? The interesting thing also about this shape is that you can have a bunch of truncated versions of the same enumeration problem in which you imagine having a roof that has a certain position and you cannot go beyond that roof when you enumerate things by non-intersecting paths. So you have all these smaller domains that you can consider. So there's a family of domains. And when you compute the numbers again by SLVNO, it's not rocket science, you see this triangular property that the numbers are saturating to Pn minus 1, because if the roof is higher, of course, you don't see its effect. Okay, so the next sequence is this 1, 4, 60, etc. Okay, so that were my 4 examples of domino tilings. Now, for vertex models, okay, so long story short, but you have a graph, right? And you consider maps, so edge configurations are just maps from the set of edges to some target space. And a vertex weight is just a functional which depends on the edge configurations adjacent to a vertex. Okay, and then the partition function will be the product of those weights. Okay, so how to think of this in terms of lattice paths? Well, we are going to concentrate on examples of such vertex models which do have lattice path formulations. And so we're going to work in some domain of two-dimensional regular lattice, which will be either square lattice or triangular lattice. We will take as a target space just a sign, which would be the orientation of the edge. And the weight will include a constraint, which is called the ice constraint, which we'll see after. But the important thing is that we're going to consider weights that make the system integrable. Okay, so the basic example here is the 6 vertex. We've seen enough of it. My convention is, of course, opposite to all the conventions taken so far. So my paths go to the right and down, okay? Instead of in Filippo, I think they were going to the right and up, okay? But all right, that's a mild thing. And so the important thing here is the ice rule is that these orientations are such that there's as many entering arrows as outgoing arrows at each vertex. Or if you want, it allows to define dually a height variable, which is well defined around each vertex by saying it goes up or down, depending on whether you have a sort of Ampere rule, that when the arrow points right, you go up, when the arrow points left, you go down, okay? All right? So now, boundary conditions, this is these domain wall boundary conditions that Filippo was also considering. And here, you can see all these well, maybe you can't see, so that's why this thing is useful, right? These are kissing points or osculation points between my paths, so they're no longer really non-intersecting. They have this property of being weakly non-intersecting, let's say. Now, integrability will be guaranteed by a choice of weight, so I'm going to take the usual trigonometric solutions of Young-Baxter equation. But here, these weights are not stochastic. Important to say in this audience. All right. So the first result, and celebrated result, is this Ergen-Korepin determinant. So all the weights depend on an horizontal and vertical spectral parameter. Here I call them Z and W, right? They are all functions of Z and W. And so at each intersection between a Z line and a W line, you will take one of these three weights, depending on the local configuration.
Except that in the Young-Baxter thing, they're all Z.
They're all what?
They're all Z. There's no W.
Oh, Z1, Z2, Z3, right? So you can say that Z1 is Z and Z2 is W. Well, it depends. At each intersection, it becomes either a Z or a W, depending on how you look at it, right? Yes. So here there's WIs and ZJs, right? Or ZIs and WJs. And so this determinant, apart from a prefactor, which is supposed to take out a number of trivial vanishings, gives you this nice determinant expressed in terms of the weights themselves, C over AB of ZI, WJ. So it looks a bit like some sort of Gesell-Vienno, right, again, but, right, because the I's and J's are kind of starting points and the ending points of my paths, right? But it's an osculating Gesell-Vienno somehow. Okay, so the uniform limit is obtained when you take this value, 6th root of unity, 12th root of unity in these notations, and again, you get the ASM number as limit of this thing. It's a little bit of work, but you can do it. My second example is the same thing, but on the triangular lattice. So because I can't draw a triangular lattice, I draw it on a square lattice and I put diagonals, but it's still a triangular lattice. And now, if you impose this ice rule, right, the fact that there are now 3 entering and 3 outgoing arrows at each vertex, you get 6 choose 3, which is 20 configurations. And you can, of course, also code them by this time, not just osculating, but they can also be triply osculating, right? The paths. So they go again to the right and down, right? So this thing here is a triply osculating, a triple of osculating paths. Okay, so they're osculating Schroeder paths. Yeah, Schroeder paths were the types of paths that we had in domino tilings, because they had 3 types of steps, right? Up, down, or straight. And here, same thing, yeah? Up, down, or straight, if you rotate by 45 degrees. I call them horizontal, vertical, and diagonal here, HVD. Boundary conditions, so we want to mimic the domain wall boundary conditions. So the most obvious thing to do is to remember that for the 6 vertex, everything was entering horizontally and exiting vertically. So here you make everybody enter on the west and east and exit on the south and north. Okay, so that's my fixed boundary condition. Now there's a problem because this corner, you don't quite know whether it's north or west, right? It's both. So you choose. And that gives you 2 possibilities. But then these 2 possibilities are mapped onto one another by rotation of half turn. So it's just the same choice, but viewed differently. So you have now a family of osculating Schroeder paths, right, going from the west to the south. And it has basically twice as many paths as we had before in the 6 vertex. Okay? So another choice of boundary condition, much closer to 6 vertex, would be to just take the 6 vertex boundary conditions, and then the diagonals, well, somehow they are not affected, so they all just go up, okay? So it means no paths on the diagonals at the boundaries, but still inside, you have plenty of possibilities. But of course, this number is much smaller because you have less configurations. Okay, so now this thing here allows for looking at lower floor versions. So if you remember, I had an upper ceiling version for my enumeration of domino tilings. Here I have a lower floor version of my 20 vertex domain wall boundary conditions. And it's very simple. I just decide to augment the original square to a rectangle. And I just put an empty of path boundary condition here, which you can see immediately imposes that the paths that start on the bottom go up until they reach some.
Sorry, is this related to emptiness formation probability?
Is it related?
Related to emptiness formation probability?
No, not directly. No. Well, okay. We've seen something that looked a bit the same, but not quite. But that's a good question, actually. Maybe there's a way of interpreting it in that way for the 20 vertex model. Okay, I will remember that question. So, all right, so then what I have here is a pentagon, right, of triangular ice, basically. And so another enumeration problem, which now has 2 integers, right? The n, which was the size of the original square, and k, how much you pushed the floor down. And of course, there's also k cannot be, I mean, beyond a certain point, you don't feel you don't feel the number k, and so it's the same thing as before. There's a saturation of the numbers when k reaches n minus 1, I think. Okay, the last example is some special boundary conditions on a triangle. So I still want to call them domain wall. So now what you see is that this is a triangle of ice, right, of triangular ice. And now I have entering paths horizontal here and outgoing paths which are vertical here, right? And so I have 2 cases depending on parity, because the middle one is different. Okay, so that's all my vertex models. So summary of enumerations and remarkable identities. If you count the 20 vertex model configurations with domain wall 1, 2 as a function of the size, you find this 1, 3, 23, right? Which is the thing we've seen before with the Holy Aztec diamond, quarter turn symmetric. And that identity is proved. The second domain wall boundary condition for 20 vertex, which we just saw, gives you these numbers. And these numbers are in the literature, actually. And they were first considering by Parter in terms of enumeration of domino tilings. And we're talking about the domino tilings is exactly of the domains I showed you before, right? So I call them Parter triangles for that reason. And there's also this lower floor K for the 20 vertex or upper ceiling K for the parterre triangles. And there's an identification between those numbers, but that's open, especially for Pn0, which was the lowest ceiling in the parterre triangle or the square in the 20 vertex version. These two numbers are the same, but I have no idea how to prove it. But what I can prove is the opposite one, the one in which you relax the ceiling or relax the floor. Then it's another sequence that we will see later. And finally, for the triangle, it's just up to a power of 2, the same thing as the first enumeration. Okay, so that's proved also. So I want to tell you a little bit about how these things work. So I summarize all the three correspondences here, right? Yes?
At this point, these coincidences look like miracles.
Yes.
Is there any organizing principle behind that?
Okay, so I don't have an organizing principle, but what I will show later is that the miracle extends beyond just the number, but also to the Arctic curves. So what we will see is that the limit shapes of the typical configurations contributing to the limit shapes of those systems are actually related.
You don't believe that there is a bijection between
Two finite numbers of objects, there is a bijection, right? No, I'm kidding. No. I call these guys non-bijections, actually. And there's a bunch of them, right? So the first ones which were really important were found in this alternating sign matrix saga, and I'm just augmenting the set of those things and still not understanding what's going on, right? Yeah. Okay, so how do you prove these correspondences without understanding what's going on? Is by just computing, right? So on the domino tiling side, of course, you write things as determinants, essentially using Gessel-Vienot or some weight-dependent Gessel-Vienot versions. On the vertex side, you use integrability. Okay, and we've seen already some uses of integrability in Leo's talk, for instance, that you can move lines around and deduce interesting things. And we'll see that all these problems actually boil down to the Zergin-Korepin determinant. Okay, so eventually the proof is just showing that one determinant is equal to another, which is not always very easy, right? But okay, there are techniques. Okay, so now the question is how to make the weights integrable. Right? I want to have the freedom of moving lines around, right? By using Yang-Baxter. So the first thing is to notice that these triple intersections here can be resolved into simple intersections, right? By just moving slightly the diagonal lines, for instance. And if you do that, you see emerging 3 sublattices, 1, 2, 3, on which I still have the ice rule at each, I impose the ice rule at each intersection. And then I see that I can obtain weights for this problem as summation over the possible configurations of these inner arrows, right? So this lattice is called the Kagome lattice after some basket weaving technique in Japan. It's not Mr. Kagome. It's really basket weaving. It means whole something, yeah.
Have you tried to find other
yes.
weights that are not factorized into the Kagome lattice?
I have tried, but I haven't found them. So, well, the question is, what do you mean by integrable? You have to be able to move the lines, right? And as soon as you move a line, you see this picture. But, right? Okay. So it's kind of...
I see there is a difficulty, but...
Yeah.
Could be.
But it could be. Yeah, no, I agree.
It could be. A long time ago, I tried, and I did not, in a method not dependent on moving lines, but I also did not find solutions.
Okay, so here what I'm describing is Kellan's solution, right? He's a student of Baxter, and he worked on this 20 vertex. Yes.
There's 20 weights on the left.
Yes.
What's the dimension of the space of weights you get by using this Kagome lattice?
So you want to know how many parameters I'm left with?
How many parameters are you left with?
Well, if you wait a little bit, 2 more slides, and you will see. So here are my 3 6 vertex, right? So I don't write the dependence on the spectral parameters, but you see all the A1, B1, C1 depend on Z and W. All the A2, B2, C2 depend on Z and T, which are the spectral parameters for horizontal and diagonal, and then diagonal and vertical, T and W, right? So I have a dependence on pairs of spectral parameters. And now I want to define my weights as the sum over all possible inner configurations of the corresponding 6 vertex weights. So it's a product of 3 6 vertex weights corresponding to the 3 vertices. Here I have 2 configurations, so it's a sum of 2. But now what I want, of course, is that this thing is invariant under motion of diagonal lines, right? So if I pushed the diagonal line, instead of pushing it down, I pushed it up a little bit, I would end up with this picture. And now it's easy to see that the inner arrows are fixed. There's not 2 configurations like here, but just 1. So you have a relation between the cubic relation between the weights of the 3 6 vertex models. Okay, so you have a bunch of such relations. You have to solve, etc., and then finally you end up with this solution. So to answer your question, here we have 3 spectral parameters and a parameter Q, which is common to all 6 vertex models, right? So it's kind of the same 6 vertex model, right? And but I have 3 spectral parameters, which gives me well, all these parameters, so eta, lambda, and mu, right? I have these 3 parameters. Okay, so the weights that you get, they're organized like this. So there's packs of 2 and packs of 4 that share the same weights. And in total, I have 7 weights for the 20 vertex model, which I wrote explicitly here in trigonometric form. Okay?
There's no kind of difference property here?
Difference property, meaning?
Like with 6 vertex, you can write it as the ratio of 2 weights or the difference of the 2 spectral parameters.
You can see how it works with spectral parameters, right? So my spectral parameters are lambda and mu here, right? I only have 2 because this is projective, so it's up to a global. So dependence on lambda and mu, you have lambda plus mu, lambda minus mu, right? This is the dependence on lambda and mu explicitly. So I'm not sure. Okay. Now, remark is that the uniform case is covered, right? Now eta is pi over 8, so it means Q, instead of being e to the I pi over 6 like it was in 6 vertex, is now I pi over 8. Okay. So it probably is related to this 4-fold symmetry that I was looking at earlier. But okay, and then lambda and mu must have some special values, and then you get uniform weights. Okay? All right, so now, how does this boil down to the Isargin-Korepin determinant? So I want to enumerate configurations, right, of this domain of triangular lattice with those particular domain wall type 2 boundary conditions. Okay, so what I start doing is stretching things out. Okay, that's not very important, but it's something you can do. You stretch out. And then you move. You start moving the diagonals, right? So what I do is I move the upper part of the diagonals up and the lower part down, okay? And so once I've done that, I claim that's it. That's the end. Why? Because if I zoom in on any place where I had the boundary conditions here, I had 2 entering arrows, right? Now, Ice rule tells me that they have to propagate. And that's true of all the domain that you have here on the right. So everything propagates nicely. And in particular, horizontally, it propagates. And I get, at least on the east side, the domain wall boundary of the inner square now, which has gotten rid completely of the diagonal lines, and which is exactly the 6 vertex with domain wall boundary conditions, right? Now, the fact that these weights are completely fixed, right, is just a bunch of numbers, right? So here it's A2, here it's A3, here it's A2 again, etc. So you have a bunch of numbers that multiply the partition function for the 6 vertex, which now only depends on the Z spectral parameters and the W spectral parameters, and somehow the T spectral parameters have disappeared in these weights. Okay? So this is a very nice situation. So you end up with the 6 vertex. But remember, the Q was not the same Q as for the alternating sign matrices. It's a different Q. It's pi over 8 now instead of pi over 6, which means that the weights of the 6 vertex now have to receive weights 1 and square root of 2 and 1. So it's the B-type weights. When the path goes straight, you get a square root of 2. So that's the enumeration. So this sequence of numbers is just, again, an enumeration, if you want, of alternating sign matrices, but with different weights. And that's why it's not factorized or anything nice. Okay, so let me now switch to my second problem, the 20 vertex with domain all free and with floor sent to infinity. So I have to enumerate this thing on the left and this thing on the right, and I claim that the two enumerations give you the same sequence. Okay? So actually, you can compute the 20 vertex side explicitly. So that also involves Hierstergin correct indeterminate, as I will show you. And it has a very compact answer. So just like what Filippo was showing us yesterday, or maybe not showing us, but implicit in what he was saying, these things are always finite truncations of infinite matrices. So the size actually appears only in the truncation, not in the what's inside the matrix, right? So you think of this as a generating function, UIVJ, right? So you expand in series of U and V. That's an infinite matrix, right, with ij positive. And then you truncate it to a finite size, and that's the determinant you have to compute, and it gives you this answer. And so I conjectured this. And then a bunch of people, remarkably many people, started working on this conjecture. And so I think the first that did something on this conjecture was Kuchan. He came up with an automated proof a la Zeilberger. Okay? But then they decided it was not good enough, and so Kortel, Kratenthaler, and then Kratenthaler, Kuchan, and Schlosser proved this thing explicitly and gave some generalizations. On the other hand, Xiuku also wrote some interesting paper. I'll come back to this later. Okay, so the proof. I just want to show you the proof because it shows you that it's not quite the 6 vertex with domain or boundary conditions this time. It's a little bit more complicated. So we do our favorite game. We first take down now, well, we stretch. Okay, first thing we stretch. Then we take down all the horizontal lines that are below the square, right? So we take them down here. Then we take the diagonal lines above the diagonal here up, okay? So we end up with this picture. And somehow, these lines that you see here, they're trapped because they point out, whereas these point in. So you can't move them across each other. The boundary condition is kind of blocking you from doing this. Now, you can't take them away, you just leave them there, right? But you can still bend the lines. So here I have bent those lines, right? So first I get rid of all these points and all these points just for the same reason as before, because the boundary conditions propagate through the entire set of points, right? So I get rid of all the triangles, okay? And then I'm left with these trapped diagonal lines, which I straighten up. So I put them horizontally here, and then they have to exit somehow, but the way they exit, again, gives rise to a set of points where the vertices are frozen. And so you end up with this picture. Now, this picture has twice as many points here as it has here, right? And some of you might recognize the 6-vertex model with what's called U-turn boundary conditions in the nomenclature of Kuperberg. Okay, so you can think of this having some little bends going back, along which the arrows are propagated and then it doesn't matter in which direction they propagate, so it boils down to this picture. And so this is also a determinant in pretty much the same way as Isergin-Korepin, which was first found by Tsuchiya and rediscovered or adapted by Kuperberg. Okay, so because there's a determinant, you can compute. Okay, finally for the triangle, so you remember we had a triangle of 20 vertex. Now it's very easy. We just stretch first and then push all the diagonals up. And the same thing as before occurs, except that the weights that you get from here and here are not quite trivial, and they create these powers of 2. Okay, but the inside here, again, is the 6 vertex partition function. So the same thing as we got before. With this e to the I pi over 8, if you insist on having uniform weights, which you don't have to, but in the case of uniform weights, this is what you get. All right, so second part, we're going to look now at the Arctic phenomenon. So I'm going to take every single one of those models that we, okay, I'm not going to insult you and show you again the Aztec diamond, okay, so but you have it in mind. But so this is what happens with my holy Aztec domino tilings with quarter-turn symmetry. So you might be a bit surprised because after all, it wasn't very different from an Aztec diamond, right? There was this little hole in the middle and tiny little discrepancies on the boundary, right? But that's enough to change completely the physics inside, right? And so you have all these frozen domains that appear, right? And this nice fourfold symmetry, right, which makes it into a cloverleaf. Now you don't see it, but here, a tiny little hole with a cross is in the middle, right? Okay. Now, vertex models. So on this slide, I show you the 20 vertex model with domain wall boundary condition 1, 2. So yesterday we saw how to make physics with or mathematics with coffee. Here we are making coffee with mathematics. I claim that this thing is a coffee bean. Up. What face do I have in the center? So you want to see it again? It's out there. Up.
Is it liquid in the center? No, the fate in terms of solid, liquid, gas.
It's liquid, of course. It's liquid. Yeah. This is a dimer model with no such thing as periodicity or anything in the weight. It's uniform. It's a uniform dimer model. It's just that your domain is a little bit twisted, right? It has this hole in the middle and this rotational symmetry. Okay. All right. So this is a simulation, so maybe it's better if I zoom in so that you can really see what the paths look like, right? So here you clearly see 2 different frozen phases, right? And then you go a little bit further down and you see another frozen phase, which is fully packed with loops. And then inside, this is the liquid phase, right? So you have 6 different frozen phases. 1, 2, 3, 4, 5, 6. Okay. So how to actually compute? So this was a simulation here. This one is a simulation, but this one is an actual calculation. So this line that you can see or not see, these dashed lines, is actually the analytic calculation. So how do you do that? You use the method devised by Filippo and Andrea Sportiello. And so here is in a nutshell what they do. They are looking at a soup of paths, right, with fixed ends, okay, and with certain weights and in such a way that there's some typical shape forming. And so the limit shape is essentially the limit, the shape of the last path, right? So the idea is to use the last path by moving its endpoint. So you move it away here, so that it becomes away from the others. It's just as if it was by itself, okay? Now, a path by itself will tend, I mean, the most likely configuration will be a line, okay? So that's very simple. Now, where does the line start? Well, it starts among the other paths, right? And then it quits the other path and continues its own life without thinking of them, right? And you can think of now the second path as being determining the limit shape, okay? So somehow this path, right? So this path feels the presence of the other paths. And in the scaling limit, this is what you expect. You expect the top path to still be part of the soup in the beginning, and then quit the soup along a tangent until it reaches the moved point, okay? Now, if you manage to characterize the family of tangents here by using the envelope of the family, you will recover the Arctic curve. That's the idea. It's beautifully simple. So how do you do that? Well, you have to compute two partition functions. One which is a slightly different partition function of the original model, in which now the last path exits elsewhere, right? So that's what Filippo called the boundary one-point function or something like this, right? So you have to compute a boundary one-point function with z and k, and then after that, you just have a single path going from one point to another, so it's a very trivial thing to compute. It's just a binomial coefficient, basically, right? And that's it. So we have to estimate these things now in the large size n, and where all the numbers scale with n, and figure out what this point B is, right? Because once you have B, A, you fixed it, and if somebody tells you what B is, then you have your family of lines and you win. Okay, so how does it work explicitly in the 6-vertex model, right? So I have the color code, pink for the one-point function and blue for the single path, right? So I think this is pretty clear, right? You're working with a 6-vertex, but the last path now is conditioned on exiting along this line at some height k. Okay, so there's a z and k, and it's better to normalize it by the partition function. So we consider this height or one-point function, boundary one-point function, as this ratio times, and y is the partition function for the single path. Okay, so you have to estimate these things at large n and k, right? So how do you do that? Well, you use what we know about the partition function, which is essentially the Izergin-Korepin determinant formula. And so because it's a determinant, it satisfies some bilinear equations, which are called many names, Hirota or De Nano-Jacobi in this case, or Lewis-Carroll, right? I mean, it has all sorts of names. And then you have to take the limit in which all spectral parameters become the same horizontally and vertically, right? So that's why derivatives point start developing here, but it can be done. And eventually, you find that the leading behavior, so the free energy associated to your model, satisfies this nice Liouville-Toda equation, right? And so you can solve if you figure out what the boundary conditions are. And you can do the same with a one-point function. So how do you access the one-point function? You remember that you have all these spectral parameters at your disposal. So you can actually choose a different spectral parameter in the last column here and use it as a catalytic variable or generating function variable for the height, for the one-point functions with fixed exit points of the paths. So this H. So now De Nano-Jacobi again gives you now a relation between this one-point function and the partition function, which you can again compute the scaling limit of, and you find this nice differential equation, which relates now the one-point function scaling behavior to the free energy. Okay, so you can solve. And this is the answer, as I think first found by Pronko and Colomo, right? So that's the free energy. Yes?
Can I ask a question?
Yes, of course. Yes.
Isn't the partition symmetric in all those parameters along the bottom? So how do you get to stick to the last row?
So it's not important, actually. It's true. What you say is true, but it's not important, right?
So could you interpret your result?
Yeah. Because you see, you view this as a function of psi, right? As a function of psi, you can take this picture and say, let me interpret what it means as a function of psi, right? Then it's a generating function for all the objects in which the top path exits somewhere along this line, and the dependence on psi tells you exactly which k it's exiting on. So it's a generating polynomial for the various k's.
Can't you then interpret it as something going on in the middle?
Sure, you could. But now, what do you do with that?
It's not simple. There is no simple interpretation of it.
You can write it down as that, but then try to interpret it in terms of, no, but maybe that's a good idea. I don't know, I didn't try. Maybe it tells you something. Oh, you. It looks like Filippo tried everything, so ask him. Yeah, it's in the bulk, so I don't think you see anything interesting. But at least here, you can be opportunistic, right? And see you can use it, okay? All right. So here is the result. So that's F. So you will notice eta, which was the parameterization of Q. And this is, of course, for arbitrary Q, and not just for Q roots of unity or anything, right? And then there's this new parameter alpha, which is pi over pi minus 2 eta, right? So one is the phase in Q, and the other is a combination of the phase. So it's really transcendental, right? You're using both some guy and it's exponential. Right? And psi, you can integrate, like I say, by site, right? You look at the differential equation we had, and it integrates very nicely. Okay? So now that you have the psi and the f, right? So you have the scaling behavior of this guy, and now we can use what I just said, right? So these hn are actually viewed as a function of this parameter tau, which is given by basically the b weight divided by the a weight in the last column, right? As a function of tau, this is a generating function of the various hk's, or znk's over zn, right? So you extract the coefficient of tau k from here, and you get your height, your boundary one-point function. So you know exactly how this guy behaves, right? It's this what we computed. This is just by construction proportional to exponential n times kappa. So k scale like n with parameter kappa, right? And so you can estimate the large n behavior of this thing. Now, the number of paths here in the blue partition function is just a refined version of the binomial coefficient. So you do Stirling asymptotics. You get also some nice formula. You put them together. You solve the extremization. So what you want, of course, is the dominant contribution to this sum, right? So it determines for you k star, which is the saddle point, if you want, of this summation. And so it's solution of the saddle point equation. And then you plug it back in your solution, and you find your family of tangent lines, because I remind you that this k star was precisely determining for you the best and the most likely exit point from the domain here. That's what this k star was. So once you have the most likely exit point, you can write the equation of the tangent, and then the envelope of a tangent is given by the classical equations. Now you have to figure out the range of parameters, but essentially you get these two values for A and B. So you have your family of lines here, and you deduce the Arctic curve, or more precisely the northeast portion of the Arctic curve. Okay, and that's for all parameters Q, right? Not just at the combinatorial point. But if you look at the combinatorial point, here is what you get. So forget about the rest of the picture for the timing and just look at this square. So inside this square is the Arctic curve for the alternating sign matrices. So the uniform 6-vertex model. And it's made of 4 pieces of ellipse. Okay? So now, out of curiosity, you can analytically continue the northeast piece of ellipse, which we just computed, right? And you find out that this is actually the Arctic curve for the descending plane partitions. You remember the hexagon with a small hole in the middle and 2 pi over 3 symmetry? If you put it on the same lattice, right, you will find that the two Arctic curves actually coincide. So this is part of what I was announcing, that these two enumerations, apart from giving you the same numbers, could have nothing to do with each other. But now what I see is that the most likely configurations in large size is actually the same, at least coincide along a certain branch. Okay? So this is sort of a, I don't know how to call it, a limit-shaped bijection or something like this. It's not a bijection, but it's as close as we can be. And so I remind you that the large domain, the DPP, is this thing here, right? And the other one is just alternating sign matrices or just 6 vertex. Okay, so now this phenomenon we'll see happens also in the other cases. So for instance, this is just the same story, but with a triangle that I showed you before. So now I have an exit point here, and again, a pink and a blue partition functions. Okay, so here again, you can use the Isargin-Korepin with the different spectral parameters along the purple line to compute the one-point boundary, right? Boundary one-point function. And now, well, you get some different formulas for the family of lines, which are a bit more complicated, but you still get the northeast branch of the Arctic curve. So you will ask me, why do I only get the northeast branch of the Arctic curve? It's because of the way I devised this tangent method, right? We were moving one point in one direction. So how to get the rest of the Arctic curve? Because it doesn't stop there. And here is the trick. So I call it the shear trick. So there is a transformation of the model. So you take a configuration, your favorite configuration. You know already about the northeast branch, and you would like to compute the northwest and the southeast branches as well of this Arctic curve. So the first transformation is what I call VF, vertical flip. So all the vertical edges are flipped. That is, if it's occupied, it becomes empty. If it's empty, it becomes occupied. But just the vertical, don't touch the rest. Okay? So you do that. Then reflection, just flip the picture. Okay? And then once you have reflected, your diagonals are pointing down instead of up. So you have to apply a shear to make them look again like what they were in the beginning. So shear. So vertical flip, reflection, shear. And I claim that this is going to map one of the two, the southeast branch to the northeast branch. Okay? So more precisely, this is what it does to the weights, right? Take one of my 20 vertex weights, omega 4, for instance. Vertical flip, I just interchange these two, right? Because this becomes occupied and this becomes empty. Reflection, I flip. And shear, I push this up and I push this down so that my diagonal, again, is in the correct position. But now I have a weight omega 2, right? So I have mapped the weights of my system to another set of weights, right, which amounts to a mapping of the parameters. And so I can deduce the southeast branch as a transformation applied to the northeast branch. Okay? And this transformation, of course, is maybe smooth, but the problem is that the gluing at this point doesn't have to be smooth. And that's what happens. It's continuous. It has the same tangent, but the second derivatives are discontinuous. Okay, so this is the picture, right, with all the branches together. And then the same thing as before, the northeast branch at the uniform point is actually part of an algebraic curve, this time of degree 10, okay? And so you have the analytic continuation of the northeast branch here. And because of this shear trick, in the uniform case, you can get these other two branches by just applying shears to the corresponding portions of this curve. Okay, so you have something very nice going on. And you can play with this not just with uniform weights, but with general weights. You also can go to the free fermion case, in which we know things are nicer because it suppresses the interaction at the kissing points. So it becomes really like a dimer model. And you have this nice phase diagram with, again, 6 frozen phases and whatever is inside. Finally, I describe very quickly the same phenomenon happening between the 20 vertex domain hole 1 and the quasi-square domino tiling with a hole in the middle and 2 pi over 4 symmetry. So I have represented, if you forget the 3/4 of a picture, you just have my coffee bean, right? And at the uniform point, you can represent both on the same picture again, and this portion of Arctic curve is common to the two problems, okay? So on one side, we have a sort of relaxed non-intersecting path, so it takes more space, right? And here we have the compressed kissing paths of the 20 vertex model, but they share the same Arctic curve portion, at least this portion, and there's still this shear phenomenon that you can see relating the two curves. Okay, now you can play with arbitrary weights. So we have all these pictures. We have an entire host of pictures. The last problem was this Parter triangle, right? So I have put it horizontally on purpose, and here vertically. And if you represent the two domains now within their intersection, which is this square, again, they share a portion of Arctic curve, right? So they are different Arctic curves in general, but they share a portion. So this phenomenon seems to be always there in these non-bijections, okay? And here is the, if you analytically continue this branch, you get this sort of quadrifoil, which is a different curve, also of degree 10, I think. And there's a question, which is, what does this correspond to? My guess is that there should be a domino tiling problem with this Arctic curve, which is still yet to be found. Okay? All right, so I come to the conclusion. Tangent method, is it valid? Well, apart from all these examples in which it works beautifully, one would like to have some sort of general proof of validity, and in particular away from the combinatorial points, right? In all these other cases, where we observe this break of analyticity of the Arctic curve, right? Because it's made of several pieces obtained by shears, at least in the uniform case, obtained by shears of some algebraic curve, right? So there is something to be understood here. Then there's all these combinatorial mysteries, which I call the non-bijections. So among them, there's the one I haven't found, right? Which was this triangular 20 vertex, and there's this curve, and it should correspond to some sort of domino tiling of a domain, a little bit like that, but the details, of course, matter a lot, as you could see, that slightly changing the square with little indents changed completely the structure of the Arctic curve. Okay, and the last remark is the thing I haven't done here, which is the stochastic weight. So you can have a stochastic version of a 20 vertex by having essentially this last relation between the three B-type weights of the three 6 vertex models. And that's it. Thank you.